Hi everybody, this is lecture 6 and today I would like to do a quick recap of triple integrals. I would like to cover a couple of examples that are homework-like, exam-like, so problems with triple integrals. Then I'd like to move on, if there's time, to cylindrical coordinates and do at least one interesting calculation using cylindrical coordinates. So evaluate a triple integral by changing to cylindrical coordinates. Okay, so here's the quick recap. Our bread and butter for computing triple integrals is Fubini's theorem. Fubini's theorem really gives us two answers as to how we can evaluate a triple integral using operations that we already know. So these operations are single and double integrals, and there are two ways we can arrange our triple integral in terms of double integrals and single integrals. So the first way you get by working over the projection of the region of integration. So this is a solid region in 3D. You work over the projection of the solid region onto the xy plane. So this is going to be, this region D I drew down, I drew on the left. And then, so you do a double integral over D. The thing you're integrating is a function of x and y, so a function of points in this region. So and this function is the number you associate to a point x comma y is this integral along this vertical line segment on the side. So you're fixing x and y and integrating upwards in the z direction to get the over a line segment, or perhaps multiple line segments for more complicated regions. They are the intersection of the domain of integration E with the vertical line. All right. So the other approach to doing double integrals that we covered last time is, instead of doing a double integral of single integrals, you're doing a single integral of double integrals. So to use this approach, and this is the thing I'd like to exemplify today. We didn't do a practical example last time. So the first thing you do is you figure out what's the minimum value of x and the maximum value of x in the whole 3D region. So you can to figure out these values and not have to deal too much with 3D geometry. What you can do is you just look at the projection. So you just take all values of E and forget about their z coordinates. This will give you a set of x and y coordinates. You draw you draw this projection, and then you find the minimum x coordinate in the set. That's the same as the minimum x coordinate in the whole shape, and similarly for the maximum. So you find the minimum and maximum values of x in the whole shape in the whole 3D region, or equivalently in its projection. And for an intermediate value of x, you consider the x slice of the region. So you cut the region by a copy of the yz plane with the given intermediate value of x. And then this double integral can be written, can be itself evaluated by an iterated integral using the method that we've discussed before. I should also note that my discussion so far has been a little bit prejudiced towards the usual order x, y, and z. So here has been prejudiced towards this order of integration, dz, dy, dx. In fact, there are 6 different orders. You can have 3 possibilities for the for what I have here as ez, for the innermost variable of integration. You have 3 possibilities there, and then for each of those 3 possibilities, you can do the other 2 dx, dy, dz. So you can do the other 2 integrate over the other 2 variables in two possible orders. So this gives us 6 possible orders. And this corresponds to working instead of fixing, working with x slices, I could be working with y slices or in z slices. Or I could be looking at the projection of my region not onto the xy plane, but onto the yz plane or onto the xz plane. Okay, so there are multiple possibilities, but they're all covered here if you just change the names of the variables. All right, so with this recap being done, I would like to move on to a concrete situation. So let's say that our region of integration is a tetrahedron, and we're going to, in this example, work with a very particular tetrahedron. So to describe a tetrahedron, I have to tell you. So first, what is a tetrahedron? You can see it. So it's really a solid shape, solid region, whose boundary consists of four triangular faces. So tetra is for four, and these triangular faces, these triangles, they live in planes. So one way to describe the tetrahedron is to just give you equations, just to give equations for those four planes. Another possible way would be to give the coordinates of the four vertices, and then you know what tetrahedron we're talking about. So in this example, the tetrahedron will be given to us using the equations of the planes. So here are the equations. So the front face that's closest to us will have equation 2x plus y plus 3z equals 6. Okay, so I will try to convince you later on that this equation does indeed describe a plane like the one we see. Let me just give you the other equations before I make that point. So this face that's hidden from us, that's closer to the yz plane, has equation y equals 4x. The other two faces, their equations are easy to guess from the picture. So the face on the x, the face that's the triangular face that's a portion of the xz plane, this just has equation y equals 0, and the bottom face, the bottom triangle, has equation z, lives in plane with equation z equals 0. Okay, so with the equations for these four planes, there is only one tetrahedron we could be talking about, and that's the one we're working with here. Okay, now let me say why these two equations describe planes like the ones I drew there. So let's start with the easier one. So this plane y equals 4x. This is if I say, when I refer to the plane with this equation, I'm saying that the plane is a set of solutions to this equation. So you can see, so y equals 4x in two variables just gives me a straight line through the origin with slope 4. But in 3D, I'm looking at points x, y, z, where x and y live in this line, and it doesn't matter what z is. So you see, z doesn't figure in this equation, so I get a vertical shape. So it's a vertical plane that cuts the xy plane along this line, familiar line, y equals 4x. So the point is that this triangular, so because this equation does not involve z, that's the corresponding triangular face lives in a vertical plane. Okay, so I think that it's okay to, I hope you guys are convinced that y equals 4x describes a triangle like, a vertical triangle like the one I drew here. For this other plane over here, 2 plus y plus 3z, that's a little bit harder to get. But the key observation, so if you have to draw a more complicated plane like this one, the key observation is that the normal vector to the plane, so it's this vector that sticks out of the plane, like this, that's perpendicular to the plane. So if I give you an equation for a plane, you can always get the normal vector immediately, and it's just given to you by the coefficient. So you get 2 times x plus 1 times y plus 3 times z. Right, so in this case, the normal vector has coefficients 2, 1, and 3. These are all positive numbers, so you know that the normal vector lives in the first quadrant. So somehow, something like this, the normal lives in the first quadrant, and so the plane is facing towards us. Also, now I drew, so this face I drew, now the plane does not go through the origin, or may not go through the origin because the right-hand side is 6 rather than 0. In fact, it does not go through the origin because the right-hand side is 6, so 0, 0, 0 does not satisfy this equation. So it's just a translate of the plane. So it's just a copy. You just start with the plane through the origin with the given normal 2, 1, 3. Then you shift it, you bring it in the direction of the normal by some amount until you find the solutions with the right-hand side equal to 6. Okay, so the fact that you can read off from an equation the normal vector of the solutions to that equation is something we'll revisit later in our course. Can also be understood in terms of linear algebra, but I will skip that discussion. I will leave that discussion for later in our class. Let's focus on the triple integral here. So here, in this example, I will just focus on setting the bounds, finding the bounds for the integration, for the integrals, for the iterated integrals. So I won't even specify the function. Our job is just to integrate, to find the bounds in the order, let me see in my notes, in the order dx, dy, dz. So we want to set up this integral. The problem tells us our job is to set up this integral in the order dx, dy, dz. So let's do that. So we're going to do this with this slicing, using slicing perspective for setting up triple integrals. So for the z, so the outermost bound is z. It's for z. So z in this whole shape varies between 0 at the bottom triangle and goes all the way to whatever z is at this upper value. So z starts at 0 and stops at this point. Okay, but what's that point? So let's see. I know that this point lives in this plane over here. I know this point lives in the z-axis from the picture, so x and y are 0. So if x and y are 0 and this equation is true, then 2 times 0 plus 0 plus 3 times z is 6, and so z must be 2. So this point is the point 0, 0, 2. Okay, so the tallest point in the picture has z equal to 2. Now we're going to fix an intermediate value of z, and then do a double integral over the z slice. So here I'm fixing an intermediate value of z, and we're doing a double integral over this z slice over here. Right? If you fix z, you get a triangle like the green one I drew. So let's do a more so now these two integrals inside, they refer to this triangle. They're a double integral over this green triangle. I have to be able to get these bounds, I have to have a precise understanding of this triangle. So let me draw it on the side. Let me draw it below here. And let's see if I can understand exactly the equations for the three sides of this triangle. So here's the triangle. It has it looks like this. So here's the x-axis, here's the y-axis. So the triangle has three sides. The bottom side is part of the x-axis where y is 0. So this is the bottom side. And there's this side here closer to the y-axis. Closer to the y-axis, that's this guy. Remember the y-axis is down here. And there is this other side which is opposite. There's this other side over here, which in this picture is this. Okay, now let's put the equations for all the sides. So this side over here, which I said is this, closer to the y-axis, that has equation y equals 4x. And this side over here is a part of this plane. So this equation is true for all points in the plane. It's definitely true for these points which are on the plane. Right, so this is a linear equation between x and y, and involves 6 and z, which is in the green triangle is just a constant. Right, so the value of the constant tells you which green triangle we're looking at. So I'll just move this, just rewrite this equation over here. So this equation is 2x plus y, but I'll move the constants to the other side. So I get 6 minus 3z. Okay, so now I can see my triangle. Let's see, I think I'll need more geometric information to set up this integral. So this double integral over the green triangle has dy outside, so I need to know the smallest and the maximum values of y in the picture. So y, I can even start doing that. So y starts at 0 in this green triangle. So it starts at 0 down here and stops at the y value of this point. You can see this point changes as z changes, right? So you get different triangles, and this point changes when z changes. So the coordinates of this point will change. The point, the vertical, the upper tip of this triangle, the upper vertex. The coordinates of this point depend on z. Let's figure out what these coordinates are exactly. So let's do it. So I have two equations. I know that at this point, so this point lies in this line. Points in this line are the points that satisfy this equation, and it also lies in this line, which is a set of points where this equation is true. So up here, y is 4x, but y is also equal to, so y is 4x, okay? So this tells me that 2x plus y, so up here I know that 6x is 6 minus 3z, right? Because I know that this, I just plug this equation in. So at this point these two equations are true, so I'll just plug this one in there. So I get that 2x plus 4x is this, and therefore 6x is this, and therefore x is 1/6 of 6 minus 3z. That's 1 minus a half of z. And then y is 4 times this number. That's 4 minus 2z. Okay. Okay. So with this, we can set up we can set up the bounds up here. We can set up the bounds for this y integral. So the minimum value of y in this z slice is 0 down here, and the maximum value of y in the z slice is 4 minus 2z. Okay. Now let's figure out the bounds for the innermost integral. This innermost integral is with respect to x. So we're fixed, now that we're doing the innermost integral, we fixed z and we fixed y. And so we're doing an integral, so we fixed an intermediate value of y like this, and we're doing an integral in x like this. Okay, now x starts on this side over here and stops over here. So what's this number? What's the x-coordinate of this point? Assuming assuming that the fixed values of y and z. So let's see if so z has been fixed. So if I know y, in fact, if I know y, I know what x is here, right? If I know y, and I do know y at this point because y has been fixed. So x is just 4 times that, well, sorry, a quarter of that. So x starts at y over 4. Because at this point, y equals 4x. If I know y, then x must be a quarter of that. All right. Now the upper bound for the innermost integral is the x-coordinate of this point. The x-coordinate of this point, I can just move y to the other side and divide by 2. So the x-coordinate of that point is a half of 6 minus 3z minus y. But I get this upper bound over here by looking. So I know that this equation is true at this point. So I just move y to the other side and divide by 2, and then I get this to get the x-coordinate of this point. And there you go. We were able to set up this integral in the order dx, dy, dz. So next up, I'd like to consider a problem, the problem of changing the order of integration in triple integrals. So let's look at an example. So example, I'm going to give you an integral, an iterated integral. Let's say this one. So x goes from 0 to 1, y goes from root x to 1, and z goes from 0 to 1 minus y. And then I'm integrating a function of x, y, and z with respect to dz, dy, and dx. And our job is to rewrite this integral in the order dx, dy, dz. Okay, so I have to find these bounds. So we have to find these bounds. And the trick to going from one order to another is to go from the bounds in the given order to a picture of the region, and then from the picture of the region we derive the bounds in the other order. So here's how I'm going to do this. I'm going to use and interpret these bounds. I'm going to find the bounds over here by thinking in terms of the projection of this solid region. So it's currently an unknown region. What I'm going to do is first I'll reconstruct the projection of the region onto the xy plane, and then I'm going to understand. So once I know the projection and I know the bounds for the inner integral, I'm going to build up the whole solid region. So let's find a picture of this. Let's draw this domain of integration. So first, the projection, and I get this from the two outer integrals. So the projection onto the xy plane is going to look something like this. Okay, so I know that this whole region, this projection, has x between 0 and 1. So x goes from 0 to 1 on this for this shape, for this projection. And if I give you an intermediate value of x between 0 and 1, the region has the intersection of the region with this vertical line will be the segment where y goes from root x to 1. So let me draw these two things. So I'm always going to stop when y is equal to 1. And I'm going to start drawing this vertical segment when y is equal to root x. So this is y equal to x, this is y equals x squared, here's y equals root x. So it's a concave rather than convex function. So here, let me give equations for these lines, these curves. So here y is equal to 1, and over here y is equal to root x. Okay, and so our region for each intermediate value of x, I get this little vertical segment. And if I put all of these segments together, I will get this wedge I just drew. So let me just say that the conclusion is that the projection of this of the region of integration, which is a solid region in 3D, the projection of this region onto the xy plane is this wedge that I just drew. Okay, so now let's understand the region itself. So I'm going to do this, I'm going to draw the three axes. And I'm going to draw the projection. So it has a side that goes with the y-axis like this, and it has another side that looks like this. And this vertical, this last side over here is parallel to the x-axis. Okay, so the action happens above this projection. And what's going on is that for a given point in the projection, z starts at 0, and it stops at this value, 1 minus y. So it starts at a value that depends on what the y-coordinate is. If the y-coordinate is, for example, if the y-coordinate is 0, then z stops at 1 minus y. If the y-coordinate is a half, then, for example, here and here, the z stops at 1 minus half, which is a half. If the y-coordinate is 1, then z starts at 0 and stops at 1 minus 1, which is 0. So there's nothing here. So to draw this thing, I'll just draw 1 minus y on the z coordinate. So z equals 1 minus y. So this is the line where z is equal to 1 minus y. Right, you can see. So this point has y-coordinate 1 and z-coordinate 0. This point here has y-coordinate 0 and z-coordinate 1. So this equation, z equals 1 minus y, gives me a line in the yz plane, and a plane, sideways plane in 3D. And our shape lives over this projection, over this wedge, and lives above the plane where z is 0 and below the plane where z is equal to 1 minus y. So our shape looks like this. And this is the region of integration. This is E. Okay, now that we have the picture, we can go back and fill in the bounds. The outermost variable of integration is z. So for the outermost bounds, I need to find the minimum value of z in this whole region and the maximum value of z in this whole region. So z starts, as I just highlighted, z starts at 0, right? That's the minimum value of z in this whole region, and stops at this point. Here, z is equal to, so y is 0, so z is equal to 1. So this is the point 0, 0, 1. So z stops at 1. Now, if the inner integrals take place in the slice, in the z slice. So if I fix a value of z, I will get a shape that looks like this. So this is the z slice in blue. The y integral, so y, and on this slice, y starts at 0 and stops here, where y is equal to, so y is given by the z value, right? Let me just rewrite this equation in terms of z. So if I move y to the other side and z to the other side, I get the same equation, but with the variables flipped. So y is equal to 1 minus z here. So y starts at 0 and stops at 1 minus z. And now if I fix an intermediate value of y between these two, the picture is getting really tiny. The x integral takes place over this red segment. So x starts back here where it's equal to 0, and it stops here in the front where x is. So it lives on this curved shape, which is a vertical. It lives above. So this shape here in the front, just it's a cone over this vertical, over this curve over here. So the points that so these are the points in the xyz space where x and y live on this line. So for these points, y equals root x. So here, y equals root x. I'm interested in knowing where x, what's the stopping value for x, so I could also write this by saying that x is equal to y squared. Right? If y is equal to root x, then x is equal to y squared. Perhaps I should say, yeah, no, this is correct. Okay, so x stops at y squared. And this is the integral in the other order. So you see that changing the order of integration is it takes quite a bit of work. To do it reliably, you have to think geometrically. So there is no way. So you have to start with the integral in the given order, build the region out of the integral out of the bounds, and then from those bounds you draw. You get the bound. Sorry, you start with the given bounds. From that you draw the picture, and then from the picture you derive the new bounds in the new order. So I strongly discourage you guys from going from one order directly to the other without thinking about the geometry. There are not so many different things you could. So the new coefficients will be related to the old coefficients, and there are not really many different possibilities for them. So if you do really random things based on some experience and how these answers tend to look, you'll get maybe half the coefficients right, but you'll get a 100% wrong number at the end of the integral. So in my grading, when in problems that relate to changing the order of integration, getting the coefficients 100% right is much more valuable than just getting half of them right, because there is a good chance, because there are not so many possibilities for what these new bounds can be, and if there are going to be expressions involving the old ones, and if you just try things randomly, or if you use a wrong approach, you'll still maybe get half of them correct. So please do this when you change order of coordinates. Just do it using the reliable method, which is going through the picture, building the picture. This is difficult, but it's worthwhile. It's the best way to do it. Okay, so let's see how much time we have. So next up, I would like to introduce cylindrical coordinates. So I have a little bit over 10 minutes. So let me introduce to you cylindrical coordinates. They're very familiar at this point. So cylindrical coordinates. So cylindrical coordinates are like polar coordinates, but in 3D. So instead of using x, y, and z to describe a point in space, we're going to use r, theta, and z to describe a point in 3D space. So we're going to use r and take x, y, and z, just forget about z, look at x and y, change that to polar, and then put z back in. So here's the picture. So it's polar cylindrical coordinates. So if I have a point in three-dimensional space, I'm going to describe it using, let me draw it a little bit lower like this. I'm going to describe this point using the height of the point, the distance of the point to the x-axis, and I'm also going to use the angle theta around the z-axis. I think I misspoke just a second ago. So r is the distance from the z-axis, and theta is the angle around the z-axis. Okay. So so the old coordinates of the point are so the old coordinates of the point in terms of the new. So r, theta, and z are the cylindrical coordinates. The old coordinates are related to the new by the rules that x is equal to r cosine theta, y is equal to r sine theta, and z is just z. It feels a little bit silly writing this, but I'm introducing a format that we'll keep using. So in the future, the new coordinate will not be just the old coordinate again. Okay, so a crucial thing so we're going to use cylindrical coordinates to evaluate integrals, and the most important thing about that, something we absolutely cannot forget when we do that, is that dv, the volume element, which in Cartesian coordinates is dx, dy, dz. In cylindrical coordinates, it's x times dr, d theta, dz. So most of the time, you want to do the r and theta in this integrals in this order, dr, d theta. But sometimes you may wish to have dz before dr, d theta. Sometimes you may wish to have it after, where I drew it. Here's a quick picture explaining this factor r. So what we're trying to understand is if we start at a point and increase r by a little bit, theta by a little bit, and z by a little bit, if I change r, theta, and z, I'm going to sweep out a certain amount of volume, and dv is that amount of volume. But it's not just the product of these three numbers. That would be, so dr times d theta dz would be the volume of a rectangle in r theta z space. But in x, y, z space, you don't get a rectangle, you get what's called a polar rectangle. And the area of that, you get a little box, and the area of that is you have to include the r. So here's the picture. If I start at this point and increase, so here's the z value for the point. If I increase z by a little bit, I'm going to get, I'm going to raise my point a bit. If I increase r by a little bit, so this is delta z. If I increase r by a little bit, I'm going to push my point forward. So this is delta r. And if I increase theta by a little bit, I'm going to move my point to around the z-axis. Okay, now this side over here is this length. If I increase the angle by theta, I'm moving on a circle of radius r, so I'm going to move by, so if I move theta radians in a circle of radius r, I'm going to sweep out a distance of, I'm going to move a distance of r times delta theta. Now, so putting all this together, I get that the volume of the box I sweep by increasing these three coordinates. So this little box has volume approximately r times, so r delta theta times delta r times d delta z. If you pass on to infinitesimals, you get this formula for the volume element in three dimensions. Okay, so let's do a few interesting calculations using cylindrical. Let's do one interesting calculation using cylindrical coordinates to get started. So here's the calculation. So we'll be looking. We're going to compute a moment of inertia, and the shape will be a rectangle. Oh, not a rectangle. The shape's going to be a cone. Okay, so E, the region, is the cone bounded by, so let me move this down. So the region of integration, E, is the cone bounded by okay, it's the solid cone. Let me make this distinction. My apologies. So E is going to be the solid cone bounded by the following equations. So there is the plane z equals 0 and z equals 1. So this cone is going to be between these two planes where z is 0 and z is 1, so the solid cone, the boundary of it is just going to be a plain old surface of a cone, and the equation for that cone is x squared plus y squared equals z squared. And since we're going to compute moment of inertia, this the mass is important. I'm just going to say that in the units that we're using for computation, the density is just 1. One unit of mass per unit of volume, whatever are the units that we're working with. Okay, let me draw this cone so that we're sure that we understand it. So the cone it's going to look like this. Here's x, here's y, here's z. So at the top, z is 0. At the bottom, so here at the vertex, at the top z is 1. I guess I'm getting tired. So at the top z is 1. At the bottom, at this vertex, z is 0. And then on the side, x squared plus y squared is z squared. Or to rewrite this, it's useful to write this in polar coordinates. So I'm saying that in cylindrical coordinates, I'm saying that r squared is equal to z squared. Let me move this slightly up. So if r squared is equal to z squared, this tells me that z is plus or minus r. In the present case, because z is between 0 and 1, it's just going to be plus r, because the r coordinate in polar coordinates is always non-negative, and theta is between 0 and 2 pi. And the same conventions are enforced when we work with cylindrical coordinates. So here's an important observation: the theta slice. So to understand this picture, to make sure that this picture represents what we think it does, to understand shapes in cylindrical coordinates, it's very useful to think in terms of theta slices. So if I fix a value of theta, right, that's the angle around the z-axis, and I cut my plane, and I cut my solid region by a half plane that leaves, that's vertical, a vertical half plane with angle theta around the z-axis measured from the x-axis. I'm going to get this shape. In this case, I'm going to get this triangle, which looks like this. So this is r. Theta is fixed, and here z goes up. So in the RZ plane, where this slice lives, I get a triangle that looks like this. So here is the line where z is equal to r. Up top, z is equal to 1, and here z is 0 on the other side. Sorry, r is equal to 0. So you can see that the theta slice doesn't depend on theta, so the shape of this slice doesn't depend on theta, and this reflects the rotational symmetry of the shape. Okay, so now let's compute this moment of inertia. I'm going to refer back to the picture when we do it. So the moment of inertia around the z-axis is, by definition, the triple integral over this solid cone, over the region, of the distance from the z-axis squared, that's x squared plus y squared, times the density, which in our case is 1, times dv. Okay, now let's set this up. We're going to set it up in the order dz dr d theta. So that's going to be, we'll have 3 integrals. Let's write everything in terms of r and theta. So I start with integral of r squared times 1 times dv. That's r times dz dr d theta. And now let's put in the bounds for this cone. So looking at the cone, we see that it touches all possible. So so there are points in this cone with every possible value of theta. So for this cone, the bounds for theta should be 0 to 2 pi. And then if I fix a value of theta, and move on to the double integral, I'm really doing a double integral over. So this is double integral over theta slice, right, for that fixed value of theta. Here I have the picture of the theta slice. So we're doing it in the order dr dz. So, sorry, dz dr. So r goes from, so the minimum value of z in this shape, of r in this shape is 0. The maximum value of r in this shape, in this triangle, this slice, is 1. And so I'm integrating r from 0 to 1. And if I fix an intermediate value of r, the z integral, the innermost integral, happens in this vertical segment. So z starts at r down here, and z stops at 1. So z integrates from r to 1. Okay. So with all this work, we can now, we're ready to evaluate the integral, and that's what I would like to do to conclude today's lecture. So we're integrating, so let's see. So first, here's a simplifying observation. So the double integral over the theta slice, the theta slice doesn't depend on theta. The slice itself doesn't depend on theta, and the function we're integrating doesn't depend on theta. So this double integral over the theta slice is just a number that is being, as a constant, that's being integrated with respect to theta from 0 to 2 pi. So the outermost integral is just going to become, it can be replaced by multiplication by 2 pi. So 2 pi times this double integral over this constant. Okay. Now the double integral is the same. So let's start evaluating it. So r goes from 0 to 1, and then the integral in z. So the z integral with respect to z doesn't involve z. So it's just r cubed times 1 minus z minus r. And then you have dr. This is 2 pi times, okay, so the integral of r cubed is r to the 4th power over 4 minus the integral of r to the 4th, which is r to the 5th power over 5, evaluated between 0 and 1. That's 2 pi times 1/4 minus 1/5. That's 5 over 20 minus 4 over 20. That's 1 over 20. So 2 times 1 over 20 is pi over 10. So that's the value of the moment of inertia of this cone, the cone that we had before, around the z-axis. It tells you how hard it is to get this thing spinning, how much energy you need to give to get this thing spinning around the z-axis. Okay, so this is what I had to say today. Thank you so much for listening, and I'll see you guys next time.